All right, in this video we're going to go over review exercise 5 from Unit 3. Let x be a triangular distribution, or a random variable with a triangular distribution 2, 7, 7. The associated graph is given below. So what this means is, well, first of all, let's ask the question, is this a PDF or CDF? Well, looking at it, we know it's not a CDF. A CDF would have to start at 0. We're good there. Has to be 0 on or above the x-axis. That's good. But it's supposed to be one connected piece, which this is not, and it's supposed to start at 0 and end at 1, which this does not. It comes back down to 0 here. And it never actually gets up to 1 anyway. So it's not a CDF. Could it be a legitimate PDF? Well, if it is, the graph is on or above the x-axis. Okay? And, okay, it should have an area of 1. Well, let's look at it. The base goes from 2 to 7, which is a length of 5. The height, reading off the graph, is right here. The maximum height of that is 0.4. So the area of a triangle is 1/2 base times height, which is 1/2 times 5 times 0.4, which is 1. So it is a legitimate PDF. The 2, 7, 7 means that this is 0 to the left of 2, 0 to the right of 7, and the PDF then basically is one piece or maybe two pieces in between that, which basically has a triangle under it with an area of 1. The highest point is given by the x value of the highest point, the mode, is given by that third number, so it says the highest point is at 7 right here. So that's enough to completely identify which one this is. And in fact, you could be able to take that information and actually come up with the formula for that particular PDF. In other words, the formula for this line or line segment that's here at the top. In this case, why would you need the formula? Well, you need the formula to be able to determine heights. But in this case, since I have a nice grid that we can pretty accurately read values off of it, we do not need the formula to find the heights. We can read them off of the grid. Okay, so let's see if you can work through these. Write these problems down right here and see if you can work through all of these right here. Come back when you're done. We'll take them one at a time on the next few slides, but you need to go ahead and write them down and try to work all of them right now. Okay, so notice we have some probabilities that we're finding and illustrating. So what's the probability that x is less than 3? Okay, here's 3 right here. So we want the probability to the left of that, which is that area to the left under the PDF graph. So we're just finding the area of a triangle, 1/2 base times height. The base goes from 2 to 3, so 3 minus 2 is 1, so that's the base. The height, here it is, it's PDF of 3. So if we had the formula, we could plug 3 in the formula, and out would pop the PDF of 0.08, which is this vertical distance of its height. Since we can actually read values off the grid, I can see this height over here as 0.08 as well. Okay, 1/2 of 0.08 is 0.04 times 1 is 0.04. And so that is that probability, 4/100ths, or 4%. All right, the probability that x is greater than 7 is 0. The probability that x is less than 2, or anything to the left of 2, would be 0 as well. All right, how about between the probability that x is greater than 5? Well, that's the probability that it's going from 5 on up forever. Well, forever might as well be 7 because there's nothing beyond 7 to the right in terms of a non-zero probability. So we're finding the area of this right trapezoid here. Now, we could use the formula for the area of a trapezoid, but we can also do this just with areas of triangles. So it's the total big triangle area minus the unshaded area of the triangle here. Now, we know that big triangle is area 1, so that's pretty easy. So it's just 1 minus the area of the unshaded part. So it's 1 minus 1/2 base times height. The base of this unshaded triangle here goes from 2 to 5. So that's a length of 3 for the base. The 1/2 is part of the formula for the area of a triangle. And the height we can find by doing PDF of 5. If we had the formula, we could plug in 5. Here we can actually go up and read the y value off. Turns out to be a nice number there, 0.24. So 1/2 times 3 times 0.24 is 0.36. Subtract that from 1, which is 0.64. So the 0.36 is the unshaded triangle, and the 0.64 is the area or probability that we're looking for. Probability x is less than 4. Again, another triangle to the left here. So again, 1/2 base times height. So 2 to 4 is a base of 2. And the height here we can read off the grid, which is 0.16. Well, half of 2 is 1 times 0.16 is 0.16, so 16%. Here we're going the probability between 3 and 6. Okay, so again we can do it as triangle minus triangle, triangle area minus other triangle area. Now this time we're not going all the way out to the big triangle of area 1, but we're going from the triangle with the base going from 2 to 6. Find that triangle area minus this little unshaded area here on the left. So in both cases it's 1/2 base times height, just different bases and heights. So for the big triangle we're going from 2 to 6, so that 6 minus 2 is 4 for the height, or for the base, and the height it's right here, the PDF of 6, which is 0.32. So 1/2 times 4 times 0.32 is 0.64. That's the area of the big triangle. The area of the little triangle, let's see, the base goes from 2 to 3, so that's a base of 1, and the height is here at the right end above 3, which is 0.8. 1/2 times 2 is 1 times 0.08 is 0.08. And so that's the unshaded triangle. The part we're looking for is bigger triangle minus little triangle area, which is 0.64 minus 0.08, which is 0.56. 56%. So we've seen in this problem and the previous one, how we can start with some fairly simple shapes of our PDF. Horizontal lines for the shape gives rise to what we call a uniform distribution. And a slanted line segment shape, like this one, gives rise to what we call a triangular distribution, and areas are easy to calculate. So uniform, the probabilities are areas of rectangles, and in the triangular distribution, they're areas of triangles or things that we can get from adding or subtracting triangular areas. The big thing to notice here, though, is that when you're dealing with the PDF, probabilities are areas between the curve and the x-axis. Very important concept.